Hi everybody, Mouse here with another video tutorial. So we have a rigid body physics controller. It's a bit more involved in setting this up. We can jump. We can now also interact with other rigid bodies in the environment, which is really the whole point of having a physics engine. We've also got set up in here non-stick walls, non-stick player character. One of the problems with breaking physics is that in games, physics aren't totally realistic. So we give our character the ability to jump and then start moving. In real-world physics, you have inertia and you jump, and that's the inertia that carries you in a direction. You don't change your velocity while in flight, unless you got like a jetpack or something. But you can do that in video games. That's how we fine-tune the input and we get our character. Get our character up on the cube. It'd be very difficult to do that with realistic physics. But one of the things that happens with that is we break collision. So now we can constantly apply force into something like a wall. And what that would do is basically let us stick to surfaces. So this here, I'll show you how we solve that. Also the camera controller. We've got in here a real basic camera controller that allows us to zoom in. Nothing special, it's not turning off the characters. It also gives us collision with the floor and the walls. So if we back up, here we go, see we're inside the wall as opposed to it blocking our view. And it's just a really simple way of handling camera, especially in a game in third-person perspective or first-person perspective. Well, I guess first-person you wouldn't really have to do it, but this will also allow you to do first-person. Guess we should turn those off if you can't see the objects they're attached to, huh? Yeah, that's a subject for another tutorial. We also have from the previous tutorials attached to our objects the health controllers, the health bars. So we go player. You'll see we have the health bar here, and I can just grab the health percent and change that. That's in a previous tutorial if you're interested. Go back and check that out. So let's get to it then. So the first thing to be aware of, the changes here to the player are the player needs to have a rigid body, and the capsule collider has a material, a player physics material. So if we go over to our physics materials and look at that, you can click on the question mark book, and that'll bring up the documentation in Unity. This material is very similar to ice. It has very little friction, it passes very little friction, and it takes in the minimum from other objects. So that way the character sort of gets a little bit of a slide on surfaces. But that in itself isn't enough to solve the problem. This helps when we interact with like bumping into other things, so we don't stick to them. Or well, they don't. They sort of have a rolling effect. We roll off of stuff. Really nice with that. Smooths things out a little bit. So then we go look at the player character. Here's all the options for the graph. There's actually quite a bit here, because this is a graph originally developed for a big, huge tutorial, which I'm now going to start piecemealing out. So there's a lot of stuff to this one. One of the special features of this character's jump ability is that they can glide. Where's can glide? Can glide. So let me show you what that does real quick. I was playing with things like multiple jumps and wall jumping, and this is just one of the easy ones, so I left it in there. Right now we've got jump. When we release the jump button, which is spacebar, it cuts the jump short, and then we have a maximum arc, like our jump height that we're going to calculate. And so the jump height, then we can jump up to that maximum. So we just put in a number, how high are we allowed to jump. And in this case, jump height is 0.5. Well, minimum jump height, where is max jump height? Max jump height is 3. So, you know, if we set it to 4, we'd be able to jump 4 units. Just going to go back here. There we go. Space bar. So now we're jumping a lot higher. Player back in there. We're going to actually look at glide really quick. So we're going to check can glide, and that's going to give us the ability to glide. So what gliding is, if we continue to hold the space bar during a descent, it's as if we have landing thrusters or like a glide cape or something. Maybe we're a flying squirrel person and we can, you know, glide all over the place. And then once again we turn that off. And oops, boy, I love the spacebar in Unity focuses on whatever the mouse is over. But you'll see we can't do, so the glide has been turned off. We behave normally. Even though we are jumping 4 units high, we aren't flying all over the place. So let me back out of that here. Okay, so real simple. I left glide in as a bonus treat because this was taking so long to make. I thought you guys would enjoy a little extra special character control setup in this tutorial. All right, so we got that part covered. The next part is we get all of our input data from the project settings input. One of the things that makes developing Unity so easy is gathering the input for a PC or Mac or a web player game has already been done. And they've set up a bunch of defaults. So we're going to use the horizontal, which gets the left and right keys, also A and D. We're going to use the vertical input, which gets the up and down and S and W. We're going to use jump for the character, which is spacebar. Then we're going to use the mouse X and the mouse Y to control the screen. So all this stuff's already been set up, and it definitely makes developing a lot easier. For more information, of course, on the input manager, you just click the little question mark book up there and take you to the documentation. You can define as many inputs as you want, give them any names. It's really quite useful. Downside is you can't define inputs while the game is running. So you got to make sure you do all this beforehand, and then you have to wire up everything appropriately using the input name. So when we use the mouse manager, or sorry, the input manager, we're going to use mouse X, mouse Y, mouse with a space, scroll wheel. So I'll show you that really quick here on the camera. We also have the camera controller in here. So the two scripts that we're going to be focusing on are the camera controller and the player controller. With the camera controls here, I've got some exposed variables, mouse, because we want the input mouse Y, and you see we're using the string mouse Y and the mouse X and the mouse wheel. In the player controller, since this is just a really quick example, and there was already so many things in here, I didn't put that in, so you can't change them from an exposed value, but you can change them from an exposed, which are internal value in the graph. So that covers that part. I think we got most of the stuff. Oh, the next is uScript user types. There are a few types we're going to use in this. We're using the, right now it's set to Unity engine.gizmos, even though we're not really using the gizmos in this one. The Unity engine vector 3 we need, and you need to put in the Unity engine debug. I'll show you these graphs really quick in the video, but I'm going to post the graphs as pictures, so it'll be really easy for you to recreate this using those pictures and take your time and really look at them and try to understand what's going on. I also spent a lot of time commenting them, so let's get into it and I'll show you them really quick. Okay, so quick overview. This is the Rigidbody physics character controller. And there's quite a bit going on here, which is why I've taken the time to comment it all. And we're not going to cover it all in its entirety in the video. The pictures will be posted, and then you can take the time to read through the comments. If you have any questions, post them on the forum. Just a really quick overview. Exposed variables up top, quick little descriptions. We're going to turn off the physics. So you see that right here, we're turning off gravity. Well, not off physics, we're turning off gravity. Just for fun. It doesn't need to be done. But we're going to turn it off so I can show you later in the graph how to calculate gravity and put it back in if you needed to. So, basic overview, we get our input on update, and then on late update we process the inputs. So any tweaks or changes we need to make looking at that data, any other things we need to grab, and because movement is a physics related event, we do it only in the fixed update, which is where all your physics are calculated. We are going to make a nested graph, the rigid body collision flags, that's going to help us get some information we need to process moving around with a rigid body and not sticking to walls. So what's really important here is the touching and grounded, and we're also going to supply the side contact points, which we get from the collision event here, which is a list of all the things we're in contact with, but the only one we're really concerned about to fix the sticking is any sides of our character that's touching. So real quick overview here then in the physics update. We're going to get variables that we need. In this case it's the gravity. We're going to get the owner's position and the owner's up. Stuff, real basic stuff real quick there to start doing our processing. We use the axial inputs that we collected up here. So you see we use jump and horizontal and vertical, and then we put those values into an axis. And so we're going to check real quick to make sure the transform, we're going to transform the movement into direction using the owner. So we're basically just going to take the horizontal axes and the vertical axes, and we're going to make a vector 3, and then we're going to put that vector 3 through this transformation using the transform. And this is, a reflected node. So to get that, reflection, actions, Unity engine.transform, as you'll see there. And so we're going to have Unity engine transform already in this list. There it is. And reflections. Transform direction is the node. So there it is, transform direction. There's a couple of those in here. And the cool thing with any reflected nodes is you can get those by adding them. So you can get them to show up by adding things to your uScript user types. So they're usually Unity engine dot whatever class you want, and then if you click on the book and go to the scripting reference for Unity, there's going to be tons of stuff that you can reflect, classes for everything. So it's very useful to know that you have that option. You can expand this, and I'll show you some of the expanded, like debug isn't in there, and neither is gizmos. And I'll show you some of those here in our other graphs, in the nested graphs. So basically, we're going to check really quick to make sure that the if needs to be, the vector is normalized. So the length of our move direction, if it's greater than 1, we're going to make sure it's set to 1, but if it's less than 1, we skip that and we just move on. We need that grounded variable. Basically, whether we're grounded or not determines the logic we're going to use when moving the character here. And this is where it gets a little bit crazy. So if we are grounded, then the assumption is we're on the ground. We're going to set some flag variables really quick. And then when you're grounded and you're not landing, or like I said, this is pretty crazy. Take your time and read through the comments. If you're not landing, then you're grounded. And the idea was to put in a gap for a landing animation, so you couldn't just jump the moment you hit the ground. Your character would have to, poof, and then you could jump again. It gives a little bit of a pacing. That way, if the user is still holding on the jump button, they don't get an immediate jump. You give them a little bit of time to release the jump buttons so the character doesn't like jump stutter. And then we start jumping, we're going to calculate our jump speed, which is also another nested graph that we're going to talk about, because that uses our maximum jump height, and we calculate a velocity that will allow us to reach that height. So we're just going to cover, like I said, all this stuff really quick. It's been commented. Then we apply the move speed, and we move through to the vertical speed. Basically, here, yeah, the movement, we take whatever the speed is, and we multiply the vertical speed by the movement. And then the movement threshold. Basically, if there isn't enough movement, like if you're moving a fraction of a fraction, we just call it 0 and stop the movement. Anything other than falling movement or gravity movement. So that way when we go over here and we apply the velocity to the object, and then we apply the gravity, the character won't, slowly kind of sputter around if there is a teeny amount of input being applied. They'll stop dead. And right here's where we calculate gravity and apply it. So we get the mass from the game object from our owner, and then we use the gravity that we pulled earlier using the gravity node, so like way over here in this first node, we get gravity, so we use get gravity and we just stick it in a variable because we're going to access it a couple times through this craziness here. And then all you really have to do to apply gravity back in, once you've turned it off, is multiply that gravity times your mass, and you get the added force that you have to add to an object in the y-axis. So that's pretty simple. So one of the branches I want to cover really quick here, because I know this looks crazy, but just take your time and read through it and follow everything. uScript is pretty self-documented, which is kind of cool. And it's really easy to look at stuff and figure out what's going on, so don't get overwhelmed. If we're not grounded, so if grounded is false, we check to see if we're touching. And here's where we get rid of the sticky walls. If we are touching, we use the side contact point. We're going to generate the point's location and normal. We're going to normalize it because it could be a vector that might be longer than 1. Okay, so the next thing we do is we take the normalized contact normal from the contact point, so we normalize it, and we're just going to add it to our move direction. So now if you remember over here, we normalize the move direction, and this note here, we transform it so that the move direction is facing the direction of our object. And we get the direction of our object from the camera. So right here, we take the owner's, to position the Euler angle, right? The X and the Z. And then we get the rotation and position from the main camera, which we've passed in as a value. And then we use that as the Y rotation for the quadrant right here. We set the Unity engine.transform, which is the rotation of our owner. So that sets the y-axis of the character. And then right here, we're just taking basically the y-axis, the rotation of the character, and we're transforming these to the horizontal axes and the vertical axes so they're facing the same direction as the character. Make sense? And then, so what we're doing here is that contact, whenever we're hitting something, the direction in which we hit it, we get a normal. And we take and we minus the normal, so the direction of the wall that we're touching, from, or we don't minus, we add that, which, neutralizes it, which is kind of cool, because it's Cartesian coordinates, the math. So, if we have a negative, the normal is pointing the other way of the direction that our character is pointing. So our character is pointing forward, and the wall that we're hitting is pointing backwards. The normal is pointing in the opposite direction. So adding a negative, we subtract that value from our the surface that we're hitting. So it reduces the velocity what we're going to input into the move direction. And so then we're right here. This is where we're talking about the debug, Unity Engine debug, and because this is an exposed value, see Unity Engine debug because we added that to our Unity user prefs, and we're going to use that to draw a line, which is pretty cool. I'm going to show you that here after we talk about this graph. I'll go show you the debug lines. Actually, we're going to talk about this graph, and then we're going to talk about the calculate jump speed, and we're going to talk about the what is it called? The Rigidbody collision flags, and then I'll show you the debug lines. They're very helpful. They don't need to be here. Some of you could remove, but I like leaving stuff like that because it'll help you when you're designing your graphs figure out what's going on. Usually, it gives you a little bit of visual output. So if we're hitting the wall, we check to see if we're jumping. After we've fixed basically, if we're touching the wall, we need to go ahead and fix that so we're not putting energy into the wall, even if we're on the ground, or we'd still stick to the wall. But if we check then if we're jumping now, because we're going to go ahead and calculate we're going to do the logic for gliding and falling. And we basically are setting a bunch of states here for animation. So we check, if we're jumping. Once again, like I was saying, it's a little crazy, so take your time and follow the lines, read the documentation. I'm going to kind of, gloss over these because there's a lot going on here, and most of this could be stripped out for a simpler game. But basically, if we're jumping, we're going to calculate if we've reached the apex. If we've reached the apex and we're still holding on the jump button, over here where we start falling. If we're still holding on the jump button and we're falling now, we check to see if we're gliding. If we're gliding, we skip the can glide. But if we can't glide, we go ahead and we jump into applying all the movement that we've calculated. If we can glide, then we go ahead and calculate the new glide value. And there's a time smoothing for glide, so you don't just abruptly stop. It eases into the glide, which then changes our y velocity using the glide gravity modifier. And then from there out, we go back into applying our move speed. So, like I said, this stuff is pretty straightforward. Then we just apply all of that, like in the previous tutorials. So we need to look at our calculate jump speed really quick. So let's do that one. Yes, let's save the changes. I think I moved a node, so it's got to save those changes real quick before we. All right, so here's our calculation, and you see the math here is really simple. It's 2 times the jump height times the negative gravity y equals the jump speed. So we get the gravity, we inverse it, that makes our negative gravity, right? Then we're gonna, I'm sorry, inverse float. We pull the y out because we don't need to do all that. We inverse the y, that gives us our negative value. Then we multiply the gravity times our jump height, and then we multiply again. So we multiply the jump height by 2 right here. Then we multiply the result of that, which gets us multiplied by the value we inverted, and then that here the square. Sorry, it's the square. Not a math genius, so I can't explain exactly what square does, but it's going to get us the proper value. Because I'm an artist, so a lot of these equations I find online by doing a lot of research. And I can't, like I said, I can't totally tell you how the math works, but it works. So, and that gets us the jump speed that we need to arrive at that apex. So, if we continue to hold down the mouse, we'll arrive at a height of 3 or a height of 4 meters. or 4 units in Unity, and then we go ahead and pass it out. So this is a very helpful little node we made. Calculate jump speed. I made sure I named it down here and put in a description. So when we look at our graphs, and there it is, calculate jump speed. We get all that information. Really cool nested node, very useful, or nested graph. Now real quick, I'm going to jump over to, here's this graph. It's rigid body collision flags. I'll load that up. Okay, rigid body collision flags. All right, this is a bit more complicated nested graph. So we'll go over it real quick here. We have 2 inputs. We need to know when the collision is exited, so we can reset everything, and we need to know when the collision is on stay, which means that they're consistently inside it. We don't really process anything on collision start. We don't really need to do that. So what we've got here first is we reset. So we make none true on collision exit. Then we reset the flags. So all the flags are false when we exit. And then we go ahead and send the output here if we were just doing an exit. So we take the variable, the flag that we're using, and we basically, if it's true or false, we then drive that value out. So the none, and then we drive out the below, above, sides, and then here's our output from the node. Now if we are staying, we get a stay event. We use the target to get our targets up position from the get. This is a great node, the get position and rotation. If you scroll down in here, you see you get up as a choice. So you turn that on and you tick the box, and there you go. We get the up, because in order to determine if something is hitting above or below, we need to at least have a point of reference. So from the collision, then we get all these contact points, big list of them. Everything that your collided object is touching is in that list. And we're going to loop through it. So we take the first contact point, current contact point, as we loop through, and then we're going to get the components of that, because we need the point that the contact occurred at, and we need the normal. And I print those out here using the debug node. Really easy, so we can see what's going on. Just give us a little bit of feedback when we're developing, especially 3D math, so we can see what's happening. Basically, then we take the dot product of the normal and the target up. So the normal, the hit. And so the normal is the direction that the surface is facing, and then the up is the direction our character's up is facing. So it's 1 in the y-axis, right? And then this is going to be some other crazy number, like whatever direction we're facing stuff in. And then we just compare that to, it's a pretty good description here too, I think. But we compare it to the, basically to a number value. The dot product is going to be a positive number if it is below, or sorry, that's going to be greater than 0.5 if it's below. It's going to be less than or equal to 0.5 if it's on the sides or below. And then we check here, we say if it's greater than negative 0.5, then it's on the sides. And then if it is less than negative 0.5, it's above. It's some pretty crazy math. Like I said, I'm an artist, and I did a crap ton of research on the web to find equations for this and adapt them into uScript. So I can't give you the super mathy, math geek version of it, but that's the basic gist of it. It should be enough to get you going. When we go through here to the output, basically if we get to this phase, we know that we're touching something, so true has to be false. We just haven't figured out what we're touching, if it's the sides yet. So for instance, if the current touch position, and we decide that it's above, or sorry, it's below, we pass that out here, and then we set below as true. And then the same thing, if we determine a touch is on the sides, we go ahead and set that as output, and then we say it's true. And then when we've gone through this little if statement, we jump all the way back. We jump all the way back to the in, which will advance the list. It drives, the for each, and that'll give us the next position in the list, the next contact point, and then we process it through there again until we run out of contact points, until done iterating, and then we come up here and we pass out the flags, and then we go back to the out. So that's how this works. It's really quite simple. Let me jump back into the game and show you what we get. So back here, I'm going to press play. Now, debug stuff only shows up in the scene. It doesn't show up in the gameplay. So since I have a timer on these, I'm going to run around. I'm going to bump into stuff. I'm going to jump on the wall real quick here to build up some data. Okay, and then let's go back to the scene. And now we can see everything that I've touched. So the red gives us the contact normal, and then the green is the correction that is occurring. So based on our hit input. So you see those are the two lines that we're putting out. Like I said, red is coming from our nested graph, and the green one is coming from the correction. So the really interesting part here is you'll see that if I turn the camera, we get these different directions, right? So we jump back real quick here. We can zoom in and look at that. So you see where I'm hitting it dead on, it's pointing it straight back out. But then when I hit it at a funny angle, the green is showing me what's being changed to give me a nice slide around the wall in that vector's direction. So that's kind of what's going on here. Real simple rundown. Really quick, we're going to go over the camera control script, and then this quick overview, video overview will be done, and we'll try this new format out where most of the comments will be done in the graph written form. It took me a bit longer to do, but I think it'll be a lot easier for you guys to read through. So we're going to go down here to the camera controls. Make sure I click on the right one and load that up. Okay, so let's do a quick overview. Camera controls. There's a lot going on here, but it's definitely simpler than the Rigidbody physics. And so let's start up here. First thing, like before, all the variables are up top with little comments on what those exposed variables are for. This is based off an older graph, so there's some other ways of doing this, but really simply, we're going to check to see that our owner has a camera field of view. And if it has that variable, then we verified it's a camera and that this is in fact on a camera. If it's not, we send out a little warning like, hey, just a reminder that this component needs to be on a camera or it ain't gonna work. But this can also be adapted to make other things float around using input around the character to orbit them. The initialized variables, basically, we're going to get our look at target's position, we're going to use that, and the owner's position, and we're going to use that to calculate the angle that we're looking at, and so the rotational angle and the distance that we're going to start with. And then right here I'm just setting the sensitivity. This is, like I said, leftovers. This graph and the other one were pulled from a much larger video tutorial series I was working on. It was just too big, too overwhelming, so we're going to do small ones. And that one supported tablets and multiple sensitivities for using, the web player and for sensitivities in the tablet. So there's some remnants of that hanging out here, but it's all pretty much just web player right now. We're going to focus on little bits until we build up to a big game. So we're going to talk about getting the axes. These are the variables, the exposed variables. So we use that string to get the axes, and we're just going to put that value in the distance axes. 0 is the number for the left mouse. So we're going to check to see if the left mouse is being held. If it's being held, that variable will set the lock mouse cursor, which turns the mouse cursor off. It hides it and it moves it to the center. It doesn't really lock it. but it sort of makes it clean. You don't have a mouse spinning around everywhere as you're turning. It makes it nicer. Then we just check to see if that is true. Then we go ahead and get the input axes for the mouse X and the mouse Y, and we stuff those into horizontal axes and vertical axes. And then if it is false, meaning they aren't pressing down the mouse button, we're going to go ahead and set those to 0. And that prevents us from using old data. That way, as long as it's up, it's 0. We do that all on update. And then on late update, we're going to process this data. These are pretty straightforward. There's just limits when you're rotating and moving. So we're going to go ahead and handle that input data. So we take the distance data, we're going to multiply it by our sensitivities, and that gives us a little magic number we can tweak and make the camera move faster or slower as it zooms in and out. And then we clamp it. We got a minimum distance and a maximum distance. And then for the horizontal, which is the rotation around the object, there is no limitation. We can rotate around and around and around and around. So all we do is multiply the sensitivity in there, and then that gives us our and we take the rotation and we add to it. So that way, it'll either add up or it'll subtract around and around and around the character. The horizontal, vertical input axes, horizontal handle vertical input axes. We have a limit to that because we don't want to be able to spin the camera over the top of the character, and then that would flip all the input axes. They'd all be upside down. The math, it just was crazy. So we limit the camera's vertical, so the ability to rotate up and rotate down to a degree here using clamp angle. And same thing, we're just going to multiply in the sensitivity, and we're going to add that, so we're going to subtract it from the rotation value. So the vertical rotation value, and then we're going to clamp the vertical rotation value, make sure it's between the minimum below angle and the maximum above angle. And then here, this used to be a nested graph, but in the Necronodicon, I decided it was so useful that I was going to turn it into a node. And so it's been turned into a node, orbit position around game object. Basically, we use the game object, we use the rotational axes and the distance from that object. So we're rotating in the vertical, rotating the horizontal, and then we get the target position as a return from that, which is really super useful, because that tells us where to position something that's floating around in orbit in our game object from that input. We do some smoothing here, which is really just to adjust values for camera smoothing. Like the closer we get to the object, the less smoothing we need. The further away, the more smoothing. Then we go ahead and, now that we've got our smoothing, we've got our new position, we're just going to set that position. We're going to put in the smoothing using dampening. And there you go. Then we get our new position, we set that, and then we use the look at with a set value of 0. Make sure the camera stays looking at the character, even though it's floating around them. Then we come back here, and again, we're going to check to make sure that there isn't anything obstructing our view of the character. And since that's a physics operation, we do that in fixed update, because all physics are calculated in fixed update anyway. So this is a little bit crazy, but if you read through this here carefully, it should kind of start to make sense. The first thing we're going to do is we're going to calculate the field of view, like a radius, using the field of view value from the camera that we got on start. And that field of view radius, what is it we do here? That we use double the character's collider radius, and we make sure that it is within the field of view. And that gives us our end view radius. Basically, we're trying to calculate how big the sphere cast needs to be. See the view radius. So you can step through the logic on this. It's a little heavy in the math. We use the player bounds. We get the bounds for the player, and then we use the extends, which is the minimum maximum of the renderer bounds So that's kind of the volume of the character, and then we use the volume of the character to come up with this radius, and using the field of view as part of that, so we can see about how big the character would be on screen. That's what we're trying to calculate. And so then the sphere cast, instead of casting a line like a ray at something like a little laser pointer, it makes a big, huge sphere. And so basically in this case, the sphere is the size of the character. And that sphere then, if it touches anything, we get a obstructed. If it's not obstructed, the camera is allowed to be at the distance, basically, that is set is the target distance, which we use when we set the position. Oh wait, I guess we do. Where do we do it? Where do we use? Hold on. I said it's been a little while. Some of these are older graphs. Where are we setting that? Ah, distance right here. So the distance that is used when we calculate, see, target distance is a different value. Basically on the physics, it's going to set the target distance to distance, which is where we want the camera to be. But if the camera can't be there, if something's in the way, we use the hit and the position of the position where we're looking at to determine, basically that's where the ray starts, that's where the character is. See the look target, and in our case is the player. So we have the distance between the hit and the player, and then we set distance to the target distance to that distance. Basically, whatever the minimum is what this does. So the minimum float. So whatever if the distance between the two here is less than the distance, that gets set to the distance. So this way, on update, the camera will move in or move out to whatever that hit distance is. So that way things don't get in the way. Remember, the camera is bouncing off the walls and off the ground. It's a sort of easy way of handling things, obstructing the camera's view. In a good game, you probably want to take it a bit further. But that's the basic camera controller. I'm going to close this. It's going to ask me to save. And then we look at the camera controller one real quick time here. Okay, so back in game here. When we click, drag, the mouse is hidden using the lock mouse node. Which, as you see, it puts it right back in the center. So when we drag down, we hit the above or maximum angle, and when we drag below, we hit the minimum angle. This prevents the camera from going all the way around and being like upside down, which would be way confusing for the player. And then we can rotate around the character now by dragging the mouse left and right. And so that's that. That's how this works. Thanks for watching the video and getting the basics of your Rigidbody character control. I'm going to post all the graphs to the forum as well, so you can follow those. Make it a lot easier to recreate this. I also have something really cool in the works, which will help you guys get the graphs in all of my examples and not have to manually recreate them. So we'll keep that a secret for now, but soon it'll be here and ready to go, and I will announce it. And again, thanks for all your support. Thank you, special big extra thank you to everybody who has donated to help make these tutorials possible and keep them free and accessible to everybody. I really appreciate what you guys are doing and showing the love, and this is how I show my gratitude for your support. I hope you enjoy and have fun uScripting.